Hello, AP Stats. Today we're going to have a short video on sampling distributions. This is Chapter 7, and we talked about this a little bit. I'm hoping the volume will be a little better with this new kind of software that I'm using. You have to see my face, which I don't love, but maybe this will help you be able to hear me better. But we remember, at pennies. We were doing ages of pennies. And each of us took a sample of different sizes. First we just took 1 penny, then we took, I think it was 10 pennies and 25 pennies, and we found out how old they were, and we graphed the average age. So we were looking at X bars of different sample sizes. This is called a sampling distribution, when you graph several statistics over and over, several different X bars from the same size sample. This is a crucial part of statistics and for inference, which we're just about to move into. So make sure you really have a good grasp on this topic. So remember the difference between a parameter and a statistic. Very important. Parameter describes a population. Remember, we can put parameter and population. Those two words start with P, so that'll help you remember it. And usually parameters are denoted with a Greek letter. Think about the parameters we already use and have been using. Mu for mean, sigma for standard deviation. We're talking about the whole population. And a statistic, it describes a sample. It is known when we have taken a sample, but it can change from sample to sample, and that's what's so important. If I take a sample over and over of the same size, every time, or most every time, it's going to give me a different standard deviation, a different mean, depending on who I get or what I get in that sample. It's our best estimate, though, to find an unknown parameter. So let's take the example, for instance, of a group of children. This will be in a video we see later. A group of 4th grade children, and we want to look at their height. So the population is all of the children in the class, say 30 children, and we can graph their heights, and that should probably be fairly close to normally distributed, approximately normally distributed. So the parameter is that true mean of their heights. Let's say we take a sample of just 4 children at a time and take their mean, the mean of just those 4 children's height. Well, that might be an estimate of a good guess of what the mean is of the whole population. Of course, it's not going to be exact. This is a point estimate, and it might be the statistic, the best estimate we might have of the parameter. Or if we take the statistic over and over and over again, another 4 children, and another 4 children, and another 4 children, and we graph all these different means, well, how is that going to look? And that's kind of what we want to look at and see if we can better find an estimate of what our parameter is. Now, of course, if you're trying to estimate a parameter of only a mean of 30 children, that's not hard to find anyways. But if you have a really large population, of course, that's when this is going to be very valuable. So let's think of those statistics and parameters that we have already learned. The one we use by far the most is mean, so make sure you write down your notes. Mean. The statistic is X bar. Actually, I should probably put that on the other side. Statistic over here. X bar, and the mean parameter is mu. So the true mean of the population is mu. The statistic from the sample is X bar. Standard deviation, the statistic is S, standard deviation, and the parameter is sigma. Let's see, slope. Slope using a least squared line. Remember, we call slope B. And now, slope parameter, the slope of a huge, well, it doesn't have to be huge, but the whole population would be called beta. It's a B with a little tail on the end. And y-intercept. Y-intercept we've been calling A is a statistic when we have a sample in our least squared line. But the true y-intercept of the whole population would be alpha, which looks a little bit like a fish. And then the last one, and very important, is looking at a statistic and a parameter for a proportion. So you want the proportion of something. The statistic is called p hat because it's an estimated, and the parameter we're going to be using p. Now sometimes, since everything else, notice the rest of these are Greek letters, sometimes a pi is used for that, but of course we use pi as an irrational number, so we're going to use p instead of pi in this class. So statistical inference involves using information from a sample to draw conclusions about a wider population. We've known that from the beginning. Different random samples will yield different statistics. So like we were saying about those 4 children, each time you take 4 children, you will be getting a different X-bar, a different average height. We need to be able to describe a sampling distribution of possible statistic values in order to perform statistical inference. So looking at all the possible X-bars in this case. We can think of a statistic as a random variable because it takes numerical values that describe the outcomes of a random sampling process. So, in other words, all the different heights, all the different X bars we're getting, we can think of as a random variable. And so, therefore, we can use probability distributions like we did last chapter, in chapter 6, to manipulate those. So here's our population, our sample. We're going to collect data from the sample and get a statistic and to make inference about the whole population. Now, sampling variability. This basic fact called sampling variability, the value of a statistic varies in repeated random sampling. Obvious, of course, each time we take that mean height of 4 children, it's going to vary from sample to sample. So how do you really get a good estimate of what the true height is if you have a really large population? To make sense of sampling variability, we ask what would happen if we took many samples. Sample again and again and again. How can X bar be an accurate estimate of mu? After all, different random samples will always produce different values of X bar. This will be our sampling distribution. So here's a good example. A sample of possible X bars and all possible samples of 2 random digits. So we're taking random digits from 0 to 9 and all the different ways we can pair those up if they're chosen randomly. And then we find their mean. So over here we have 0 and 0, and their mean of course is 0. And down here on the far end we have 9 and 9, and their mean is of course 9. And in between we have all the combinations. So notice the X bar, of course, that's occurring the most is going to be all these 4.5s through the middle. 4.5 is the average of this 5 and this 4, but as well it's the average of this 9 and this 0. So that's all the possible X bars we could get. And if we graph that, of course, we're going to get this histogram with 4.5 as highest and the 9 and the 0 on either end. Now, is this a normal distribution? No, it's approximately normal, but not that close to normal. Just because it's mounded and symmetric doesn't mean it's a normal distribution. So notice for every sampling distribution, going to have some sample size. Here our n was 2, but we could have done a sampling distribution choosing 3 numbers and finding their X bars, finding their means. The sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. So these are all the possible X bars we could have gotten in this particular experiment. Make sure you know the difference between a population distribution, a sample distribution, and a sampling distribution. It's so important. There are actually 3 distinct distributions involved. The population distribution is, of course, the whole population. It gives the values of the variable for all individuals in the population. The distribution of sample data shows the values of the variable for just one individual sample. And of course, the sample size, we can decide what that's going to be. And the sampling distribution shows the statistic values from all possible samples of a given size. So this distribution is all your X bars, all your P hats, some statistic taken over and over from the same sample and looking at that same type of size and looking at that distribution. Here it is in a picture. Here we're taking, for instance, marbles, red and blue marbles out of a bowl, and the color. So this is starting out as definitely a categorical variable. So the color here is in the first graph, the population distribution. We have 100 red marbles and 100 blue marbles. And so our true parameter, our true proportion of either one is 50%. So then we look at all these different individual simple random samples of size 20. On the first one, you get 8 red out of 20. So our p hat, our parameter, is 8 out of 20, or 0.4. On the second simple random sample, we got 11 out of 20. 0.55 is our p hat. Our point estimate, our estimate of what the true parameter is, just taken from that one sample. Then we do it another time, a different random drawing of 20 marbles, and we get a p hat. How many reds out of the whole thing? 13 out of 20, which is 0.65. So notice the sampling distribution is all the different p hats that we get put on a graph. Well, notice that shape looking quite normal, approximately normal, but all the different p hats, and notice that it centers on what the true proportion is. We know here that the true proportion was 50%. We don't always know what that true proportion is.